Okay, welcome to the third part of our algorithms tutorials. The first thing you'll want to do is go ahead and get the Intro to Algorithms Part 3 PowerPoint and download that so that you can follow along. The lecture part, I think, won't be too long for this section, but there's a fair amount of tricky stuff in here, partly because this is the first time we'll be introduced to recursive algorithms. So basically functions that call themselves. It's kind of mind-bending in sort of an Inception kind of way, and you'll see what I mean in a minute. But go ahead and get that downloaded, and I will start sharing my screen. And right, so in the last section, we were working on this problem where if we're given a pattern length, so a value for k, and then some text, we had to figure out what were the most frequent words or frequent patterns in that string. And basically that's quantifying how many times each pattern happens in the text, and then figuring out what's the maximum value, and then returning the patterns that match that maximum value. And you should have by now solved it in two ways. The pattern count way, using our very first function that we built, the pattern count function, but then also the dictionary method. And so I just want to show you how you can compare the speed of those two things. But the question, really the whole point of introducing these recursive algorithms is helping to see that it matters how you solve a problem when you start having to deal with genome scale data. Okay, so the efficiencies of the computational method that you pick, or the algorithm that you pick, really makes a real world difference. And it's a huge research area in bioinformatics. So even for this simple case where we're just counting words, you'll see where you know, the approach you take can make a really big difference. So what's the runtime of this algorithm? I'll show you in a minute, but just trying to think about conceptually, how do you answer that question? Like not the literal number of seconds, which is what I'm going to show you how to measure in a second, but think about how this algorithm works. Right, it has to loop across this whole text, and every time it gets a pattern, it has to search the whole text for that pattern. Right, so for every text to the k-1, right, that's basically our window, it has to slide along text to the k-1. So roughly 27 times 27, or however the length of our text is squared. It's making a lot of trips across that text in order to count the k-mers. And obviously, right, the most obvious ones, these ones that we had colored red, it's counting those multiple times. It's scanning along the text for the same exact k-mer. And then even once you've counted it, you've still got to take one more trip, because we've got to figure out which ones are the maximum, and then, right, scan along the list and count all of those. Really, when you're talking about the length of text squared, this one time down the loop doesn't make a huge difference, right? You're just kind of adding one on there. So a lot of times, you know, if you were talking about how fast is this algorithm, you would say it scales as the length of the text squared. Okay. So then, if you think about it, you know, we're talking about texts that are only text or DNA sequences that are only a few hundred maybe 1,000 base pairs long. Genomes, though, are much larger than that. And so it would be nice if we could scale this in a way that didn't have an exponent here, right? So rather than multiplying this times itself, could we figure out a way to make it scale as just the length of the text, something linear, right? Even the length of text plus the length of text, right? That's just 2 times across the whole thing. That's not so bad. That's not as bad as, think of the human genome. Rather than having our 1,000 base pair DNA Rosalind problem, we've now got 3 billion base pairs squared. Okay, that is going to take a while to just do a simple task like count the number of times ACGT happens in that genome. A 4 base pair window, a 4 base pair pattern. So then I suggested that you do the dictionary solution. Okay, this one shouldn't have been too hard. It built on things that you already had to do in other Rosalind problems. And so what's the runtime of this algorithm? Well, in a minute, we'll use the time function in the terminal to actually run these things and get the number of seconds. But if you think about it in the same way we did for the pattern count method, what is this algorithm doing? Well, it's sliding along the text one time, and every time it gets a new window, it's comparing it to what's in the dictionary. So early on, this comparison goes really fast because the dictionary is not very big. So this is really only scaling as, say, the length of the text times the size of the dictionary. Okay. So, oops, forward. If we think about, well, that second loop, then when we have to get the maximum, is really only looping across that dictionary one time. It's kind of like in the previous thing where we had to go across the length of the text one more time. In this case, we just have to go through the dictionary because we've eliminated, all of those patterns that don't exist. So we only have to look through our dictionary one time. At most, if we think about how big could that dictionary be, the number of possible combinations or the number of possible patterns that could exist is 4, because it's ACGT, raised to the power of k. So how big are the k-mer patterns? If you want to have k as 3, so you're just looking at 3 base pair patterns, then the maximum size of that dictionary is 4 to the 3rd, right? Because there are 4 base pairs, and then 4 base pairs, and then 4 base pairs. You just 4 times 3, or 4 to the 3rd power is the total number of ways that you can put 4 base. 4 to the 3rd is the maximum number of ways that you can put 4 base pairs in a pattern that is 3 base pairs long. It's a mouthful. It's better than text squared, right? Because, well, it's better than text squared as long as 4 to the k is less than the length of the text, which is almost always going to be the case, right? Because k is the size of the pattern or the window size. And as long as 4 raised to that power is less than the length of the text, we should be okay. And even yeah. Won't go too far down that rabbit hole. This algorithm is also nice because that 4 to the k, and this is, again, don't want to chase this too far, but natural DNA sequences are not random combinations of ACGT. For example, coding sequence is constrained to the codon table, right? The amino acid translation table. Okay, so you would expect to see some patterns highly overrepresented. So you don't, in other words, it's not just a random set. So that dictionary is not really growing as 4 to the k. That's just the maximum it could be. But the dictionary does get big, at least potentially, right? I just give some numbers there. If you're looking at, if k is 15, there are still a billion patterns. Now, whoops, what just happened there? There we go. Which, right, that's still less than text squared for a human-sized genome, where the genome is 3 billion base pairs long. So that still would scale better. So anyway, let's look in real-world terms at how fast are these things relative to each other. So just got my terminal here. So this is my solution for, this is one of the downloaded data sets, but it doesn't really matter because I'm going to run it on the same data. But this is the pattern count method, and I used the time function, and then this is the name of my Python program to count k-mers using the very first method where we use our pattern count function. Okay, so it took almost 0.3 seconds. Not a long time, so you might think, oh, that algorithm's fine for what I need. And if your genome is small, maybe it is. But let's see what happens. So this is the dictionary version. And the dictionary version took 0.05 seconds. Right, so that is a major increase. Right, both of them happened in the blink of an eye. So on again, 100,000 base pair genome, no big deal. But if you scale this speed increase up, right, this is a monster increase in speed. All right, so question is, can we make it faster? Right, because we're still going text times basically the size of the dictionary. The bigger the dictionary gets, the slower this thing will be. So is there a way that we could just make it scale as the length of the text? Well, to do that, we need a way where we can slide across the text, and rather than have to compare it to the dictionary, we could just count the thing as we see it, right? So a solution, for this would be if we could convert the k-mer into a unique number where we know that this pattern corresponds to this position in the array, right? So we convert the pattern into a unique index value for the array. Then every time we see the pattern, we just convert it to its index number and add one at that position. We don't need to check if it's already in there at all. We know it corresponds to a unique position in the list or in the array, and so we can just add one. Then we, just like the other ones, need to know what's the max value in that list, and then we can convert the index value back into whatever that pattern was to return the original pattern. So we need to figure out, is there a way, and obviously I wouldn't be asking if there wasn't a way, to convert patterns into unique index values. Okay, And this is the coolest, I mean, one of the coolest things that I've come to appreciate in bioinformatics and about the sort of real computer science side of um, bioinformatics. So this is just kind of a cool puzzle. If you think about how can I convert any pattern of DNA sequence into a unique index? Well, some really smart person figured out that if we list them all alphabetically, and so what I've got here, and this slide, I know it's kind of busy. If you start out, just look at the patterns here. So I've listed all the 3 base pair patterns in alphabetical order. So AAA, and then basically just the last one that I have colored black is the only thing that's changing, and then it's cycling. So I have ACGT, and then I switch the second one to ACGT. And the thing to notice is that's cool is that if you take off the last base pair, all of the remaining stuff stays alphabetized in order. Okay, and why that's important will become clear in a minute. So if we assign a value to A, C, G, and T, and here I'm going to call that symbol to number just so, right, already you can see that's going to be a part of a function. We just need to know how to assign a value to each base pair. And so we'll do ACGT in order, and the ordering is alphabetical, right? A is 0, C 1, G is 2, T is 3. So we just assign to that last base pair whatever its value is, and then we just need to know how many sets of 3 base pair motifs came before this. Okay, so in this first section, right, where the first 2 base pairs are AA, there are none that come before this. So how many sets came before this? So before the AA section, 0, right? So we don't have to add any value to the 0, 1, 2, 3 that we get from the ACGT over here. So that is the number value for those first 3 base pair, those first 3 patterns. Okay, then we go into the second set, right? And how many sets came before this? So in the AC group, we have 1 set that came before it, right? The AA group came before it. So 4 times 1 means we need to add 4 to the value of the last one. So the ACGT still gets a 0, 1, 2, 3, but we know there was a set before it, so we need to add 4 to that. Okay, and you can continue to walk through this. Same thing here. How many sets came before AG? Well, there were 2 sets. How many came before AT? Well, there were 3 sets. And so we have to multiply 4 times however many sets came before it, and then add that to the ACGT value. So in this case, 8 plus 0, 1, 2, 3, and 12, 0, 1, 2, 3, and that carries on. So over here, right, I just ran out of room, so I had to move over 1 section. Now, right, I've got everything where the middle position changed, ACGT. Now I moved on to the first position, and I'm getting the C. And I could, right, these would still be in order if I took this list, right, and stuck it down here, right, I would just be counting down 15, and I'm picking up on number 16. There were 4 sets of 4 before this in alphabetical order. So 4 times 4 is 16. For an A in the last position, I add 0, so that's position 16, and so on, okay? So we can get the number for any, and this isn't unique to 3, but I'll stick to 3 for the example. For any k-mer, we can get the corresponding number by just assigning the value to whatever the last position is, and that'll be called a suffix in the text. So I've color-coded suffixes as black and prefixes as red. So the suffix is just the last thing, and that's the only thing that we really know, like we're directly assigning a number to that, right? A is 0, C is 1, G2, T3. Then for the prefix, we just need to know how many sets of 4 came before this, right? So in this case for CC, there were 5 sets before it. So now the question is, well, for an arbitrary k-mer, how can we know how many sets came before it? Well, this is where it gets really cool. So how many, come on. Whoops. And so what I've done here is just taken, let me go back here. And so our list of 2 base pair prefixes, all I've done is take those 2 base pair prefixes, and now I have a list of 2mers, right? Dimers, whatever. And we can do the exact same process where, okay, if for AA, right, what's the value of A? It's 0. How many sets came before this group? Well, 0. Right? So everything that has an A as a prefix had none that came before it. And so we just add 0, 1, 2, 3. Okay, and then we get to the second list, and there's only 1 set of 4 that came before this. So 4 times 1, and then add the ACGT. And so, right, this is the cool thing. Now notice that the numbers for these 2 base pair patterns correspond to the number of sets that came before it in the 3 base pair patterns. So, right, keep that in mind, and when you're on your own, you can flip back and forth. But for example, CT, if we look, right, that number is 7. So let's go back here to our 3. CT, how many sets came before it? 7. So we know the prefix to add on that 3 base pair pattern if we know the number for CT. And that, now we can chop 1 more off, right? So now we've only got A and C as our prefixes. Let's run the same algorithm on that. Well, now there's no prefix because all we have is 1 letter. And so we can assign that a value, 0 and 1, and notice that the number for these 2 is the number of sets in the 2 base pair pattern, the number of sets that came before it in the 2 base pair pattern. I think that's just kind of cool. And so, but that gives us the basis. What we've just kind of walked through is a recursive algorithm. We're basically doing the same algorithm, just chopping 1 letter off at a time and calling itself. So how does that play out? Let's show one that we could figure out from the table that we had, CAG, right? We could go back here and look, where is CAG in this table? Okay, it's right here. The number for CAG is 18. Okay, but how would we get there? Like, how would we tell Python how to calculate 18? Okay. Well, the prefix for that is 4 times the number that came before it. Now, we don't automatically know how many came before it, but we just noticed that the k minus 1, so in this case 3 minus 1, so the 2mers, if I knew the number for the 2mer CA, then I could fill this in and get the value. Okay, so, well, what's the number for the 2mer? Well, I'm not sure yet. In this case, you know, we have the list right here, but for an arbitrary one, what is the number of sets that came before CA? Well, I'm not sure yet. So let's take one more letter off. And so now I'm down to the C. There's no longer a prefix. So I know everything in this equation. The value of C is 1. So now I know, right, 1 is the number of sets that came before in the tumor. So I can fill this back in. 4 times 1, and the A is gives 0. Sorry, there were 4 sets before it. Then this 4 can get plugged back in here, right? That CA was value 4. And then, right, we'll go back here just to show the CA, right? There were 4 sets that came before that. So everything making sense. And now 4 times 4 is 16 plus 2 is 18. Like magic, we just figured out exactly in alphabetical order where CAG is supposed to fall. And so that can be the index of a list. So position 18 in that list is corresponding to exactly CAG. Okay. So now let's just play with one that we don't know, right? What about GAT? I did not extend this to get the last 2, right? I would have to do 2 more columns, one that starts with G, one that starts with T. So we don't know automatically where GAT is supposed to fall. So this is essentially the algorithm that we've been doing. 4 times the prefix plus the value of the suffix. So symbol to number is the thing that I keep having in this little box. That's the thing we know, and the prefix number, right, is this little thing that we can't figure out right away, but if we call the same algorithm one at a time, sort of chopping it down, at some point we're going to get to this single symbol, and then we can work our way back. So for GAT, right, we start out with GAT, but we don't know the pattern to number. We don't know the prefix value for GA. Okay, so we walk it back one, get what's GA. Okay, we don't know where in the big list how many sets come before GA. So we send, whoops. Send it down one more level so that now we only have G. Okay, and now our pattern to number function, right? How many sets come before it? Well, there's no prefix anymore, so we can assign the value of G. So symbol to number is 2. Now we have a value here. That's how many sets came before GA. So 4 times 2 is 8. And we're adding 0 because the A value is 0. So now we have 8 sets that came before GAT, and then the T gives us a value of 3. So our total number here, so the number that corresponds to GAT is 35. Like magic. And I just put this in here just to show you, right? Okay, so this one not laid out in my columns the same way, but this alphabetically goes across. Okay. And I put in some values just so you don't have to go blind counting those things. But GAT in the list is at position 35. So in some ways, that's all you need to know. You just need to implement that into Python. And so how do you do that? Well, you're going to write a new definition, pattern to number. By new definition, I mean a new function. And right? So you're going to have a sliding window that's feeding patterns into this function. Okay. And actually, that's getting ahead of myself a little bit. So the pattern, we just did this function by hand in some way, right? What the pattern is GAT, and then this is the algorithm right here. Why this is called recursive is because when you call, okay, so you're calling pattern to number on GAT, but then part of the function of getting the pattern to number is using pattern to number. And then that has to go down until it gets to the pattern to number not evaluating to nothing, right? So when it gets to the last step and it has a single base pair, there's no more prefix. So, right, we're feeding it the prefix every time. So when you look at the pseudocode, the first thing it does is say, if the pattern contains no symbols, right? What does that look like, right? Something like if pattern equals double quotes, right? Nothing in it. Then it's going to return 0. Okay. So thinking about this pattern, right? When it gets here and this is blank, this is going to be 0 plus 2. And then it's going to feed 2 back into there, and so on. Okay, and then notice this is backed out. So that only happens when it gets to that last base pair in the pattern, or really the first base pair in the pattern, because it's walking backwards, right? So GAT, when it gets to the G, this is going to return a 0. But remember, right, it returns a 0, but it evaluates to a 2 because G, the symbol to number is G, into that, calling this pattern. I think I'm potentially being more confusing there. So how do you get, in the next step, the symbol equals last symbol pattern? So really this is saying, how do you get the last symbol from, say, GAT, right? How do I get the T off of that? And so that's the new Python trick that I'm showing you here. So if I want to return a T, I can do symbol equals pattern and then brackets -1, because when you use negative values in the list slicing notation here, so in the brackets, it starts counting from the right to the left. So -1 means it takes off or returns just the last thing on the pattern. So if pattern was GAT and I had this code, symbol would be equal to T. And same thing with prefix. So what do we want the prefix to be? Right. You might define prefix equals pattern from 0 to -1. And that will work, right? Because in this case, we want to get the GA, that's the prefix. And -1, remember, Python is not inclusive, so it's not actually going to get that if you specify it, if you have a start and an end. The reason this one works is you haven't specified a start position, right? It's just a shorthand if you want to return one value, because you're right, you'll have to think back all the list cases you've done. If you just want to get one index value, you just say, give me the pattern and then that index value. Okay, so that hopefully gets you to the pattern to number solution. To solve the bigger problem, right? Our goal is to have a faster way to count words. It's not enough to just be able to convert these things into their correct number, right? So now we've got a list where we know we have patterns. We've got to be able to then go the other way around from numbers back into patterns. And so, it may take some time to think about what's going on in this pattern to number. Like I said earlier, this idea that a function can call itself and basically get in its own loop until it solves something and then basically works back out to give you the final value that's the inception kind of thing. You're going layer by layer, and then coming all one layer out at a time. We can do the whole thing in reverse though as well. So if we know what the number is, right? So in our case of GAT, we know the number is 35. So if we're given the number 35, how do we recover what pattern that belongs to? So in this case, we do, the number is 35. We just divide that by 4, which is 8. The remainder is 3. That tells us it's a T. And so now 8 becomes our value. We divide by 4 to get a 2. There's a remainder 0 in this case, so that evaluates to an A. And then we have 2 divided by 4, 0, with a remainder of 2. Right, 2 evaluates to a G. And so we're left with GAT, right? Because this is if you think about it for a while, you'll see this is just really going in reverse of this process right here. Instead of multiplying by 4, we're dividing by 4 at each step and just kind of walking our way back down that process. Here I'm giving you just that notation, right? If you use the percent symbol, so the index here, for example, 3, and then a percent symbol, which as an operator, it's called a modulo operator. This would, on the first time, this statement would be 35 modulo 4, and the remainder would be 3. So here, this variable remainder, given this function on 35, would return a 3. And then to get the symbol, right, we have to have a number to symbol, just like we had a symbol to number, right? If we go back one, our symbol to number was if we have an A, give it a 0, and so on. Now we've got to have the reverse of that, where if we have a 0, we need to return an A. Okay, so you have the pseudocode there. And then one more thing is that to solve the frequency array of a string, and I talked about this in class last Thursday when I was going over some of the coding on the board, or actually I was showing it in Spider. But to solve the frequency array problem, if you start counting k-mers, or if you run the pattern to number and start trying to assign values, you'll get errors because the list doesn't yet exist at all those positions, right? If you get a GAT window and try to add one to that index value doesn't exist in the array yet in the list. I keep using list and array interchangeably. So does the textbook. They're the same thing, or the same kind of data structure. It's just one list. So the way to initialize an array or a list that has all the possible index values for the patterns that we might see is to just make an array that is 4 to the k long, right? 4 to the k power is the maximum number of patterns that you could get. And so if you just make a list that has 0 as the value for every position in the list, then when you go to count your patterns, those positions do exist in the list. And so you're just going to add one every time you see it. That's the frequency array solution. And so I've given you the code here for those that weren't in class. So if you say list equals and then put a 0 in brackets times 4, and then this is the exponent operator, 4 to the k. What this is saying is make a list that is populated by zeros. So every position is going to have a 0. And then when you use the multiply sign, it's saying make it that long. Right? If I put a 6 here, I would get a list that is 6 items long and they all have 0. So just not sure this is clear. Right, so list example equals 0 times, and I'll just say 6, and then print list example. Right, and so the output, right, is a list that is 6 long. Okay, and what I'm telling you is for the frequency array problem, you need it to be 4 to the k power, except obviously you're going to have to define what k is along the way, but let's just make it, right, let's say k was 2. Right, now we've got that same list populated by 0, but now it's 16 items long, right? 4 squared. So whatever k is will determine how long is that list all populated by 0. And now you run your pattern to number, and for GAT, for example, it's going to say, okay, then go out to number 35, index 35, and add 1 to it. And so in principle, hopefully you kind of get the idea that this ought to be faster because we're only having to go across the text one time and every pattern is going straight into the list and being counted. We don't have to check whether it already exists in the list. We just add one every time. So that's that line right there. Okay. So once you've solved the number 14, generate the frequency array of a string, try to go back and solve problem 11 using the frequency array solution and see which one is fastest. Okay, I won't spoil it by running it for you. We'll maybe talk about it in class once some people have this one solved. Didn't look like in Rosalind. Some people haven't solved 11 yet. If you haven't solved number 11 with either the dictionary or the pattern count, you are falling behind. I didn't assign them to be due today because I knew we were going to do the frequency array, and so we're going to go back and hopefully have you solve number 11 with the frequency array solution. I would love to see, when I look at the code that you have to submit with your solution, I would love to see the frequency array solutions in that code. But at the very least, you need to be getting through you should be through number 11 already, but if you're not, yeah, you have some work to do, because these are not trivial to make work. They're not difficult once you sort of understand what needs to happen. But they can be challenging to implement. Okay. All right, so you should, by the time you get finished with this section, part 3, you should have done all the way through number 14 in Rosalind. Let me make sure I have the numbering right. Yes, okay. So you should be able to finish number 14. All right, that's it. Happy coding.